Okay, let's look at the remaining portion of the history of the atom. We will pick up with light and lead into Bohr and other people who have studied and tried to figure out the different atom models or create the different atom models that we know today. Before we can understand Bohr's experiments, we first need to review. Some of you may have already learned about the electromagnetic spectrum, but for those who haven't, we will go over how light relates to the atom and its electron. First, let's understand that the electron was believed to have a property called wave-particle duality. So there's a particle theory of the electron as well as a wave theory of the electron. When an electron acts like a particle or matter, it is considered the particle theory of the atom. When the electron acts like energy or behaves like a wave, we consider it to be that theory of the electron. So depending on how you are studying it, the electron could be considered a particle of light or a wave of light. So when Bohr did his studies, he saw it as a wave. So the electron has a wavelength, a frequency, and has energy. So let's review a little bit. Wavelength has this symbol of lambda, or it looks like an upside down Y. We measure it from crest to crest, or from trough to trough, and we use wavelengths. The unit will be nanometers. For frequency, we measure it in hertz or per second, and it is how often the wave occurs. So if you look at these two waves, you'll notice the green wave has a longer wavelength than the purple wave. And the purple wave has more peaks in it in any given wavelength. So if we drew a line in two areas of the waves, we could count the different amount of peaks. So the green line has less wavelengths and occurs less frequently because those wavelengths are long, and the purple one has a very short wavelength, so therefore it's more frequent. There is a relationship between wavelength, frequency, and energy. You'll see on the left side, the longer the wavelength, the lower its frequency, which also means that there is a low energy. If you look on the right side, we see that a short wavelength has high frequency and also has high energy. So let's think about this a little bit. If you have somebody who is tall, like 6 foot tall, and then you have maybe a child who is 7 or 8, and a little teeny tiny dog, like a miniature Yorkie, and they are going for a walk. If the man is doing his normal stride and trying to have like a decent pace for his walk, you'll notice the little boy, his stride is shorter and he looks like he's moving faster. Sometimes he could even look like he's almost jogging. And then if you look at the little puppy beside him, the puppy is like running to keep up. That dog is taking so many steps to walk that same distance and using a lot of energy to do it. So if you think about people walking, somebody with a long stride, maybe walking a nice comfortable pace, and then somebody who is shorter with them has to walk a little faster because their steps aren't as big. And then you get those little teeny tiny dogs. They always look like they're running when people are out walking, especially if they're out taking a brisk walk. The other thing we want to remember is that radio waves are our longest wavelengths. So when you think of AM and FM radio, That's what we are hearing are their wavelengths. And microwaves, we use them for cooking, are the next longest wavelengths, so they're second in line when we're going from longest to shortest. Infrared has a shorter wavelength, and infrared is actually heat. So if you think about some of our newscasts or different TV shows, they show helicopters hovering over areas. You see that red light, so they're using an infrared detector looking for heat in areas where people may not be visible or living items may not be visible. And then we get to the visible spectrum. So the colors for that are red, orange, yellow, green, blue, indigo, and violet, and we use Roy G. Biv to help us remember those. So red is going to be your adult with the longer wavelength, and violet is going to be your little puppy dog that is running along with the shorter wavelength. We move to ultraviolet light, so we have UV light, and that's what we're worried about with the sun emissions and skin cancer, so we have to watch for those. X-rays are the next in line, and many people kind of forget. Almost everybody has had an X-ray. Usually when I ask you guys this question, has anybody never had an X-ray? Somebody always raises their hand, but we forget when we go to the dentist. They take an X-ray every year to look for cavities. So X-rays are what we use to help detect cavities. So they're a very short wavelength. And then we have gamma rays, which is energy. So gamma rays are very powerful for us, but very tiny wavelengths. So light as particles, okay, we just went over light as waves. So light as particles. Light is made up of discrete bundles of energy. We can call them photons or quanta. And that amount of energy in each quanta depends on the light color. Or we could say it the opposite way. The light that we see is dependent upon the amount of energy that is in that wavelength. So the amount of energy is related to the colors of light that is seen, and each quanta represents a color of light. We're going to finally move into Niels Bohr. Niels Bohr studied light and wanted to determine how much energy or the wavelengths of each color of light. Okay, Niels Bohr his study, he took an element and ran electric current through the elements. Light was emitted and light went through a prism, and different colors of the rainbow were observed, or the element spectra is what we would call that. So when we see that rainbow on the end, that's called a spectra, and the study of light is called spectroscopy. When all the colors of the light are present, you will see a continuous spectrum, or what we call a rainbow. So as you see in the image, there is electric current on the left side. It's being hooked up to an element, and it's going through a very fine slit so that way it can concentrate that light as it goes through a prism. That prism then spreads the light out, and you can see the rainbow for that particular element. A line emission spectra give information about atoms and their specific energy levels. So different gases in a tube could produce different sets of lines, and we call this an emission spectra. So a very similar procedure was performed. You can use a diffraction grating for this, and we will do this in class. And a diffraction grating is like a prism with many slits, so when we see this in class, we'll understand a little bit better what that would be like. And only certain colors of the light will appear. So when you have specific colors, it's called a line spectrum. So Bohr studied various elements, recorded his observations using the prism to see a full spectrum of the element, and then he used a diffraction grating and saw that there were only a few lines for that element. He noticed when he was studying the two spectrums that everywhere there were lines in the line emission spectrum, there were voids in the continuous spectrum. This is called an absorption spectrum. So in the diagram, you see that there's a void in the red area, in the green area, and then down in the blue/violet area. So the line spectrum would have lines in those areas, and the rest of that rainbow would have been voided or would have been gone. It wasn't present. So Bohr studied the bright line spectra and the absorption spectra of atoms. He noticed that there were patterns. Elements produced a characteristic bright line spectra, and the bright line spectrum was of the same colors that were missing in the absorption spectra. Here we see the emission spectra and absorption spectra of hydrogen. So this is the same spectrum of the same element, but one is being observed using a prism, so you have the full rainbow but a few voids, and the other one is visible using the diffraction grating, so most of it is black or voids and just a few lines. Bohr did most of his studies with hydrogen, and that's where he focused in his calculations. So his calculation had a constant and was just a simple math formula, but the problem was it only worked with hydrogen. It didn't work with all of the other elements that he had studied. So he did continue studying this. But what came from this, his hypotheses, was that there are certain orbits or definite orbits in which the electron could travel around the nucleus. So we get from this, and I'm sorry it's not typed in here, but you can definitely add this in your notes really big, and we will go through it in class and label it, is called a solar model or the Bohr model. So the orbits relate to the energy or wavelengths of light observed in the line spectrum. And the electrons circled in that distinct radius around the nuclei, and an electron remained in that path or energy level. So it was a discrete diameter, kind of like our solar system is thought to be. So a solar model is an appropriate name for this. So what happens is when electrons are in a high energy level and they lose energy and move to a lower energy level, you can see in the right diagram that there's an arrow with a squiggly line coming off. That's representing photons being released. So the light gray area is a high energy level, and when the little yellow electron moves closer to the nucleus, photons or quantums of energy are released from the atom. When we have the opposite, energy coming into the atom or hitting the electron gains that energy and moves from being close to the nucleus to being further away from the nucleus. So the electron moves from a low energy level to a higher energy level. Bohr concluded that when energy or photons were given off, a certain color of light was emitted. So to conclude his experiments, light is given off when electrons lose energy. So they emit their energy as light. When it goes from a higher energy level to a lower energy level. This is very important. It will definitely be a test question. When light is absorbed, when electron gains energy. So that is, it goes from a lower to a higher energy level. So keep in mind, the most important time we see light is when the electron loses energy. We lose energy by doing motion and talking, dancing, doing all sorts of crazy things. An electron, being just a tiny little particle, doesn't have all those opportunities to give off energy. So the only way he can do that is for light to come off. Our next person that we're going to talk about is Erwin Schrödinger. He based his work on many others. We're not going to go into a lot of details about those people, but there are different theories that help bring his model together. So the model that we're looking at occurred in the late 1920s, and what we call it is the cloud model or electron cloud model. Another name for it is the charged cloud model. Notice the word cloud is very important there. If you just look at the diagram, you'll notice in the center is our void. It's white, that's where the nucleus is, so there's no electrons in the nucleus. And then the rest of it is like a fuzzy cloud, so that's where the electron can be. So putting everything together, the path of the electrons are not shown in the model because electrons are that diffuse cloud, that blurry area of negative charge. So Bohr's model gave us results for the hydrogen atom, but not for all those atoms that have many electrons. So Schrödinger's atom replaced the idea of orbits with the quantum mechanical model. This model is where electrons have definite energies but didn't have definite distances or places to be around or in shapes for the nucleus. An electron with a particular energy is most likely to be at a given distance from the nucleus, but it could be other places. This is also known as the uncertainty principle. We won't, like I said, not going into a whole bunch of detail, but to help you understand that when a student asks to go to get a drink of water, we observe their pace as they leave the door, and if we keep that rhythm in our head, we can kind of guess where they're going to be in the hallway and about when they get to the water fountain. And you can picture in your mind how long, them getting a drink of water and then coming back. At any time that they're not in our view, we're really not sure where they are, whether they're walking still to the water fountain, if they started drinking water, or if they came back. We just know they're somewhere in that area. Like Mrs. Sully, every time she calls my room, she always asks, is this student there? She doesn't just say, please send this student down, because during that time period you're supposed to be in my room, but it doesn't mean that you are in my room. There's just that chance, that high probability that we could find you. And your parents have that probability that they could find you in school, but they don't know exactly where you are in the building at every given minute. So we really have no way to determine where the electron is or how fast it's moving. That nice little orbit idea is replaced with that cloud, so it's just that diffuse fuzzy looking picture, and we'll talk about how we get that picture in class and get an understanding on why that's the final picture. So the cloud is dense, where the electron is most likely to be, and it's less shaded. So as we do get further away, you'll see that outer edge is less shaded, and near the nucleus is less shaded. Okay, the atom has some major subatomic particles. We do know that the atom is not the smallest discrete thing. However, it is where it maintains its certain properties. Once we go to the subatomic particles, we have protons. So protons from every atom are exactly the same. So they're not particular to an atom. versus gold versus silver, the protons are the same between them. It's just how many protons are there make it gold or silver. Neutrons are our neutral items. Protons were positive, and electrons are our negative particles that we're focusing on. There is also the atomic number, which is represented by a Z. It tells us the number of protons for a particular element or atom. We do have isotopes for atoms. That's where they are the same element, so they have the same number of protons. However, they do have different number of neutrons. And then we have quarks. Those are tiny particles which actually form our protons and neutrons. We are not going to study those. We're going to stay with protons, neutrons, and how to calculate the atomic number and isotopes. The mass of an atom is measured in an atomic mass unit, which is an extremely small unit. It's not something we can just throw on the balance and say, hey, here it is. So 1 AMU equals 1/12 of the mass of a carbon-12 atom. So it is roughly 1.66 times 10 to the negative 24 grams. We do not have a balance that can measure that low. So the approximate mass, this is the approximate mass of a proton or a neutron. The mass number is represented by the capital letter A. It equals the number of protons plus the number of neutrons. And finally, we have the atomic mass of an element, which is the average mass in AMU of all naturally occurring isotopes of an element. This number appears on the periodic table. So the number on the periodic table is the average of isotopes. It's not of one particular atom. And our textbook does describe the difference between mass number and atomic mass very well. So we will take a look at that in class. Okay, let's review our facts. Over 99.9% of the mass is in the nucleus, and that consists of neutrons and protons. And we didn't really talk about the discovery of the neutron. That was James Chadwick doing a electron cloud chamber experiment. So we just need to know that there are neutrons, and the particles that are in the nucleus are called nucleons. Another fact is that all atoms of the same element have the same number of protons, but can have a different number of neutrons. If two atoms of the same element have a different number of neutrons, they are called isotopes. So iso is usually meaning similar. So they are still the same element, but they are slightly different because their neutrons vary. The neutral atom have an equal number of protons and electrons. If they are not neutral, they are called ions. So ions are when you either have more electrons than you do protons, or you have less electrons than you do protons. And we will look at how that happens, or diagrams of those to help understand that a little bit better also in class. Okay, we're going to look at how we represent the different isotopes of an element, or our isotopic representation. So the element we're going to use is platinum. Its symbol is capital P, lowercase t. So right there we have our symbol of the element. The mass number is represented in the upper left, so it precedes the element and it is in superscript. The atomic number is preceding also the symbol, and it is subscript or written down low. So this isotope has 78 protons. Remember that the atomic number is equal to the amount of protons. And to figure out the neutrons, we subtract the mass number. We take the atomic number from that number, and we get 119 neutrons. Our next video we'll also be talking about this, so that just gives you an idea of where we're headed with some of the atom ideas for math.